have a bit of a gap. I might do a tour check in on you guys. We're talking about radicals today. Before we start, we're going to time travel back to grade 9 with me or Miss Ansarez. Did I teach any of you guys in grade 9? No, maybe not. Yes, I did. I did teach grade 9. That's like the one time in the last 10 years I taught grade 9. Lucky you guys. You guys learned about like different kinds of number sets, like the integers and the rational numbers. A rational number is a number that can be expressed as a ratio of two integers. Last unit, you guys worked with rational expressions, one expression divided by another. Here's some examples of rational numbers. 2/3 is a rational number. So is -4/7. But you might be like, well, Mr. Smith, that's not one number divided by another. There's a negative up front. Well, remember, you can write this as -4 divided by 7. It is a rational number. Integers like 5, they're rational numbers too. But if you're like, Mr. Smith, that's not one number divided by another. Guys, how can you write 5 as one number divided by another? Right? 5 is like 5/1. 5 is a rational number. 0 is also a rational number. You can write 0 as 0 over anything. Let's do 34 for Austin Matthews. These are all rational numbers. You guys familiar with rational numbers? Nod and smile. Just to be clear, the 3M people, you guys are working on your assignment, right? This is not need to know for you, but if you're interested, you can follow along. Some numbers cannot be written as one integer divided by another. These are called irrational numbers. Do you guys know any irrational numbers off the top of your head? There's a classic one you use in measurement all the time. With circles. Pi. You guys seen the number pi before? Pi is an irrational number. You cannot express pi as a ratio of two integers exactly. You can get close. When some of you guys take calculus next year, you'll learn about the natural number, Euler's number, E. And it's about 2.718, and it kind of goes on forever, just like pi does. But there's a special kind of irrational number called a radical, where it's a root, but it's not a perfect root. The root of 2, you can't express root 2 as one number divided by another. Root 3, same thing. Root 5, same thing. Those are all irrational numbers, and today we're dialing in on the ones inside a root. We're talking about radicals. Why did I skip over? I'll even include, maybe you guys could add in. Why did I skip root 4? Why would root 4 not be considered an irrational number? It's a root, like root 2, root 3, root 5. Emily, what do you think? Yeah, the root of 4 is exactly 2, right? Yeah, exactly. And 2 is an integer, which is a rational number. It's not irrational. The root of 9 is equal to 3. So you guys can jot this down. The root of 4 is equal to 2. The root of 9 is equal to 3. The root of 64, since I listed it there, that's a little off center. The root of 64 is equal to 8. But like the idea is, these are so Gervin Lucas, you're making sure Kemper can focus, right? Kemper, you have my blessing to move anywhere if you so desire, if they're distracting you. All right. So things like root 2, root 3, root 5, irrational numbers. Root 4, root 9, etc. They are, because they're perfect square numbers. They have square roots. You guys convinced you need to put these in your calculator to see they give decimals that go on forever, or are we convinced these are irrational numbers? We're convinced, we're okay. Today is all about working with these special type of irrational numbers, which we're calling radicals today. I don't know why. There's probably some Latin reason why they're called radicals. I don't know. But today we are going to talk about some skills involving radicals. The first step is we're going to develop a nice, tidy rule for multiplying radicals together. We're going to do a little numerical investigation here. You guys are just armed with your calculators. We're going to look at these similar but different expressions. Here's the idea. Like the root of 4, hopefully you guys understand is 2. And the root of 4 is 2. And when you multiply 2 and 2 together, you get 4. Shocking, I know. But in column B, it's a bit different. What we're doing is we're multiplying the 4's first, and then we're square rooting. So this would be equal to the root of 16. Note the root of 16 is also 4. Coincidence? Who can say? Let's look at a few more of these similar operations. The root of 36, we don't need a calculator for this one, is 6. 6 times 6 is 36. What if we multiplied the numbers first? Now, 36 times 36, that is not a perfect square that I have memorized. 1,296. Of course, how could I forget? But if you square root 1,296, you get 36. It appears there may be a pattern. But what if I'm cooking the books here? What if it was only 4 perfect square numbers? Can you guys try doing the root of 5 times the root of 5? Now, you guys could literally, most of you guys are using a display calculator. Just put that into your calculator and see what it gives you. The root of 5 times the root of 5. What'd you get, Emily E? Yeah, and I mean, maybe you did not need a calculator for that, because isn't that just what the definition of square root means? The root of 5 is what you multiply by itself to get 5. So of course we got 5. What if we did the multiplication first? And just to be, for interest's sake, the root of 5 is about 2.236, blah, 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 blah. So if you actually did it, if you actually got the decimal and did 2.236067978, and you multiply that by itself, your calculator would give you something incredibly close to 5 if you actually just did it with decimals. What is 5? What if you did it by doing the multiplication first and then rooting? Well, 5 times 5 is 25. And yes, the root of 25 is equal to 5. But maybe you're saying, well, Mr. Smith, maybe this rule only works when it's the same number. Well, can you guys try the next one? The root of 12 times the root of 9. Root 12 is an irrational number. It's a decimal. We are going to get a decimal value here, and that's okay. The root of 12 times the root of 9, you can just punch it in as you see it. I got about, to 2 decimals, I got about 10.39. Did you guys get about 10.39? I see nods. What if we do the multiplication first? 12 times 9 is 108. And the root of 108, I wonder what this will be. It is about 10.39. It appears we have some kind of pattern here. Can you guys humor me and just do 2 more of these? It may be overkill. Can you guys just double check? Because, this one, the root of 9 is exactly 3. Maybe this rule works only when one number is a perfect square number. 7 and 6 sure aren't. You know what? Just for kicks, I'm just gonna write out some decimals here. The root of 7 is about 2.64. I'll just say 3 decimal places. The root of 6 is like 2.449, and when I multiply those 2 numbers together, I get about 6.48. Now, if we do the multiplication first, we're doing the root of 42. I'm guessing it probably comes out pretty close. About 6.48, it does. All right, this is now definitely overkill, but like just for completion's sake, I will finish this last one off. The root of 13 times the root of 21. Just on my calculator, about 16.52. 13 times 21 first. Of course, it's 273, of course. And the root of 273, about 16.52. Here is the point. Are you guys convinced that it doesn't matter whether you root each number first and then multiply, or multiply first and then square root? You get the same answer, right? You get the same answer either way. You guys convinced? We just showed it 6 times. This always works. This is a rule that you can use for multiplying radicals. It's like the meat and potatoes of today. It's what we're using today over and over and over again. It's a rule that you're going to need in grade 12 functions and you're going to need in calculus. The rule is this. I almost wish I made this text bigger because I don't know why I have so much space otherwise. The root of A times the root of B is equal to the root of A times B. You can multiply the numbers first and then square root. Very cool. So we just kind of showed that property is true with a little numerical investigation. Hopefully you are convinced, but we have to have this down. All right. Why are we learning this today? Well, in some situations, like finding when Bryden will roof his ball, a decimal approximation is fine. In other applications, especially for you guys going on to taking grade 12 functions in calculus, the exact value is important. Leaving things in radical form is going to be something we do a lot moving forward. We use radical form when an approximate answer is not good enough. So I have some technology for you guys. Some terminology. The first thing, we are going to refer to the number inside that radical sign. This is called the radicand. That is definitely some new terminology for you guys. This is the one day a year where I use this term, radicand. Otherwise, it's just the number inside the root. But officially, it's called the radicand. And we can now kind of give a rule. What values of the radicand will give irrational numbers? Well, we kind of investigated this on the front. Numbers that are not perfect squares. Numbers that are not perfect squares. Okay. So the radicand, the number under the square root. Next bit of terminology. Radicals come in 2 forms. An entire radical is where the entire, you can think of it this way, the entire number is underneath a square root. Things like root 7, root 19, root 34, etc. These are entire radicals. It's just something underneath a radical. It's the root of 7, root 19, root 34. Whereas a mixed radical, so it's kind of like a mixed fraction, when you guys are back in grade school, a mixed radical has a integer multiple out front, like 2 times root 7, or 3 times root 19, or -5 times root 34. These are called mixed radicals. You've got an integer part, you've got a radical part. Just like with mixed fractions had a whole number and then a fraction. We're going to keep bringing all my markers over here. It's like 1/2 is like a fraction, 2.5 is like a mixed fraction. So entire radical, mixed radical. You guys okay with that distinction there? Mixed radical has a number attached with it. All right. Let's continue. I'm losing my erasers too. Here it is. Sometimes, just like with fractions, we can actually make entire radicals simpler, making the numbers lower, coming up with an equivalent expression that's just more simple, easier to work with. And it is important for us to have a good grasp on our perfect square numbers. I have them listed here, at least the ones up to 12. Your perfect square numbers are just something, I can't apologize for it. In the 3U course, we just need to understand that 1, 4, 9, 16, etc. are perfect square numbers. Let's look at some examples. Some new tech for you guys, reducing radicals into their most simple form. Let's look at the root of 50. 50 is a large number. And we know the root of 50 is like some decimal number. It's like 7.1 or something. Can you guys see a perfect square number that goes into 50? 10 is not a perfect square number. Just start going through the list and see if you can find a perfect square number that divides into 50. Caden's got one. 25. Guys, check this out. I can write 50. Can you guys do this with me too? I can write 50 as 25 times 2, shockingly. But we just learned a new rule where you can multiply the numbers first and then square root, or you can square root each number and multiply those together. The root of 25 times root 2. We just showed over and over this property is true. Doesn't matter whether you multiply first or square root first. What's the root of 25? Exactly 5. The root of 50 is equivalent to 5 times root 2. They are equivalent in every way. 5 root 2, the numbers are smaller, more manageable. The expectation moving forward is just like with fractions, we simplify our radicals as low as we can go. This is our first example. You guys don't believe me that these are equivalent? Dude, what's the root of 50 on your calculator? Just bring up the root of 50. You don't got to write anything down. The root of 50, it's like 7.071, blah, 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 right? Can you guys do 5 times the root of 2? 5 times the root of 2. This will work. This will not backfire. This will work. 7.071, blah, blah, blah. Same thing, right? They are equivalent in every way. The numbers in 5 root 2, much smaller, much more manageable. This is the expectation for you guys in your math careers moving forward. We reduce radicals as much as we can. Let's do another one, then take some questions. 2 root 27. Is there a perfect square number that goes into 27? I'm asking rhetorically. There is. Can you guys see what it is? Flash me a gang sign with the number that... Or just participate, that'd be good too. I will assist you guys. 9 is a perfect square number that goes into 27. We can write 2 times root 27 as 2. We can write the 27 as 9 times 3. Why would we do that? So we can reduce. We can use our property from the front. That's the same as the root of 9 times the root of 3. The root of 9 is exactly 3. And I can multiply 2 and 3 together. 6 root 3. 2 times the root of 27 is equivalent in every way to 6 times the root of 3. What's the advantage? Lower numbers inside the radical. You guys have to trust me that it's useful. It's necessary. 2 in the books. Should we try another one? We're going to do this one 2 ways. Okay? Now, I'm going to do the root of 180 a little inefficiently at first, if you guys are okay with that. The the root of 180, I can recognize that 4 goes into 180. So I'm going to write 180 as 4 times 45. 4 times 45. Why 4? 4 is a perfect square. Why would I do that? Well, because then I can reduce using our cool property, the root of 4 times the root of 45. And this simplifies down to 2 root 45. But you know what? We can do even better. Can you guys see there's another, if we look at 45, I could keep going. There's a perfect square number that goes into 45. 9 goes into 45. I could write root 45 as 9 times 5. And then I can keep simplifying and keep reducing. I'm showing a lot of steps here. But that's okay. It's our initial time doing this. Of course, the root of 9 is exactly 3. And we end up getting 6 times the root of 5. We just had to do it in a couple of steps. But yes, the root of 180 is equal to 6 root 5. Now we can be a little bit more efficient by just having a bit of a think and seeing if we can come up with a more efficient way. Maybe there is a larger perfect square number that goes into 180 that we could have started with. Can you guys have a scan in that list I gave you? There is a highest perfect square number that goes into 180. Let's have a race. Can you guys, who can find it first? Okay, Emily won, but you've already helped out a lot today, so you're going to take a break. Madeline. 9 is higher, but we can do better. Alicia. 36. Guys, check this out. 36 goes into 180. That means I can write 180 as 36 times 5. How do I know it's 5? Well, just do 180 divided by 36. But look, guys, the root of 36 is exactly 6, and we get there much more efficiently. The purpose of that exercise was to show you that it is way more efficient to look for that highest perfect square number first. But if you're not sure, you can just start going about your business and doing your best. If you don't get the optimal one right away, then you just have to keep simplifying. Now, here's something fun for you guys to try. If you have a display calculator, this works. I believe if you put root 180 into your calculator and just press equals, I believe it should simplify for you to 6 root 5. I believe. Boo! No, actually, it just gave a decimal. Pretend I just didn't say anything there. Did anyone actually give you 6 root 5? Okay, so we got some lucky people. Maybe you could talk about how to share those settings in your calculator with other people. I jest, but I can probably help you guys figure that out on yours too. But that's a good way to check an answer. We're reducing radicals. Guys, just like you guys don't say, you don't leave answers like 4 over 6 anymore because you're in 3U math and you reduce your fractions as much as you can. We are now at the stage in our math careers where we reduce our radicals as much as we can. 4 in the books. Anything you guys want to chat about? This will be a skill once we're done. You guys should always be practicing. But for the U3U people, this is a new skill for you guys. It's not enough to do 4 with me. You have to practice. You have to drill as much as you can until it becomes second nature. You will get that opportunity. Let's continue. I want to apply what we've just learned to the quadratic formula. So some new, going a bit above and beyond. Now, you guys can just take my word for it. When you take this function, x squared plus 6x minus 3, if this was in the warm-up, and you went about your business, negative b is negative 6, 2a is 2, and if you calculate the discriminant, you get 48. If you guys looked up the exact roots, say in the back of a textbook or that sheet from yesterday, you would not see -6 plus or minus the root of 48 over 2 because the root of 48 can be simplified. So let's do a little exercise here together. Can you guys see the highest perfect square number that goes into 48? If you've already contributed, take a seat. But the rest of us, let's race. Who can find the highest perfect square number that goes into 48? Strong hint. It's lower than 49. Oh, so I thought you were putting a hand up. Okay, now I'd just be happy if anybody participated. 48. So here's what if I were you guys and I was looking for how can I reduce my root 48, I would just start doing 48 on my calculator. 48 divided by my perfect square numbers, and I would just stop when I get a integer number. Decimal number. Guys, what's 48 divided by 16? 3. Yes. 16 is a perfect square number that goes into 48. We can reduce. So what would that look like? Well, let me show you. And then you guys can try one on your own. We are going to write 48 as 16 times 3. I like writing my perfect square number first. All divided by 2. Now, if you guys are okay with this, you can start skipping that intermediate step. I think we understand the root of 16 is exactly 4. So I'm going to just write that right now already as 4 times root 3. Why 4? Because the root of 16 is exactly 4. You may be asking, how does that make things any simpler? Look, everybody, 6, 4, and 2, they're all even numbers. We can divide all those numbers by 2. And I'm just going to actually just add in brackets over here. Let's just divide everything by 2. -6 divided by 2 is -3. 4 divided by 2 is 2. And our exact roots from before, -6 plus or minus the root of 48 over 2, can be written a bit more simply as -3 plus or minus 2 root 3. They give you the same approximate values. One is simplified. And I can't apologize for it. This is just the day in the curriculum where you guys learn how to simplify radicals. And this is one application. Can you guys try the next one? Follow the pattern. Look for pretty, please. Don't immediately reach for 9. I know 9 goes into 72. You can do better. There's you see what it is? And try to let people figure it out. We gotta get everybody used to looking for those perfect square factors. Get out your calculators, grind it out. Yes.
Do you have a band?
I do not. But Ange at the front office might have some. But yes, 36 goes into 72. It's the biggest one we can do. We can write 72 as 36 times 2. This one's amazing. Look how simple this one gets. The root of 36 is exactly 6. We're just using our skills from the previous page. All divided by 6. And guys, look. 6 divided by 6. 6 divided by 6. 6 divided by 6. If you divide every single thing here by 6, you get 1. You get 1 everywhere. You get 1 plus or minus 1 root 2, or just root 2. And on the bottom, 6 divided by 6 is equal to 1. You just get 1 plus or minus root 2. That is way more simple than what we had up top. And this isn't me deciding to punish you guys with weird stuff. This is just the stuff we do in the curriculum at this point in the course. But yeah, we've simplified some exact roots. I think this is an appropriate amount of steps. Anything you guys want to chat about? I want to chat about one thing. If I could show you guys back to maybe example D here, what would I think reasonable in terms of skipping steps? Now, just writing down your answer because your calculator can do this. No, that's no bueno for me. I want you to convince me that you know what you're doing. I'd like you to recognize the highest perfect square. Write out this step here, 36 times 5. At this point, I would be okay if at that point you went to 6 root 5 because you've demonstrated some knowledge. But that would be my minimum expectation of you guys. All right, what else do we got? And this is what we'll wrap up with. Some applications in later courses, you have to multiply radicals together. Let's do a couple and let's tie in our simplifying tool. So you guys already know the root of 3 times the root of 6. That's the very first property we learned today. You could write that as the root of 18 using the property from before. 3 times 6 is 18. And now, after our last exercise, you guys should be thinking, can I simplify my radicals like I simplify my fractions? There is a perfect square number that goes in 18. There's only one of them. Somebody different. Perfect square number that goes into 18. Yes. 9. Thank you. So we can write 18 as the root of 18 as the root of 9 times the root of 2. And then IMO, it is fine just to say, okay, the root of 9 is 3. And I'm left with 3 times root 2. Now, for those of you people who your calculators are spitting out that exact form, if you punch in root 3 times root 6, it will give you 3 root 2. It doesn't show me you know anything. Show all your work and show those steps. All right. Let's do B together, and then I'll have you guys try C on your own. So check out B. We're multiplying 2 mixed radicals together, but that's okay. We'll just multiply what we can together. Multiply the coefficients, the numbers together. 2 times 3 is equal to 6. Multiply the radicands together. 3 times 15, 3 times 5 is equal to 15. And now the brand new U will think, is there a perfect square number that goes into 15 so that I can reduce things further? Can you guys discuss for a second? Eyeball it. Is there a perfect square number that goes into 15? I see some head shakes. I see some eyeballs in the back of the head. No, this one is done. You actually can't simplify this any further. It's just 6 root 15. That's it. I will let you guys try C, and I'm going to resist coming along for the ride for a second. Can you guys try C? And then we'll talk marching orders. Great job today, everybody. Resisting the urge to do it. Still resisting. Okay. Multiply the numbers together. 5 times 4 is 20. Multiply the radicands together. 2 times 8 is 16. Guys, is there a perfect square number that goes into 16? 16 is a perfect square number. The root of 16 is exactly 4. We wouldn't leave it as root 16. That'd be dumb. The root of 16 is exactly 4. And 20 times 4 is 80. Believe it or not, those big, messy, mixed radicals multiplied together, it just winds up being 80 at the end of the day. Fascinating stuff. All right, we did it. So I'm going to end the video here.